Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, in this segment we want to talk about more normal force problems. So remember, the normal force is the force perpendicular to usually gravity, actually perpendicular to the surface, not to gravity. So here we've got a book right here, and there is a force of gravity up, and there's a normal force, down here, and this one's up. So the normal force is going to be, in this case, positive, and the force of gravity is going to be negative because they have to have equal and opposite forces. But we want to just dive into how to solve these problems. So as we're solving these problems, it's all about free body diagrams. So here's like the tips and tricks. First of all, draw the free body diagram. Label all the forces. Expect to label Fn if there is a surface involved, right? Create an F-net statement and solve for the unknown variables. Note, if the surface is an angle, you will need to find the x and the y components of f of n using trigonometric stuff, sine, cosine, and tangent, as we see. So let's just dive into some examples. So example 1, normal isn't always up. Huh? All right, an elephant with a mass of 4,700 kilograms steps onto a platform. What is the normal force acting on the elephant? Draw the free body diagram of the elephant. All right, that's my elephant. Don't judge. By the way, so what's the first thing we've got going on right here? We've got the force of gravity, right? And the force of gravity is going to be a number. Actually, note here, is the elephant accelerating? Is he moving? He's not. So we've got two forces acting on it, and it's just straight up and down. The normal force in this case will be up. The force of gravity will be up. And if you think about this, F of n is equal to the mass times the acceleration, and this is equal to the mass times the acceleration. But what is the acceleration of the elephant? 0. So in this case, F of g will be equal, right, to F of n. All right, and we can find out what F of g is. We know his mass. We know that he weighs 4,700 kilograms. And actually, in this case, it's mg, not a, because the acceleration would be the force downward, right? And so we would just say this is equal to 4,700 times 9.8 meters per second squared, and we get 46,060 newtons. So we can actually say that both of them is equal to 4606. And actually, we should actually make a quick note that one will be positive and one will be negative. Downward, negative, upward, positive. So the normal force is actually 4606. The force of gravity is negative 4606 newtons. That's the easy one, all right? Let's now talk about how that might work, not just up and down. So now we have a magnet being held on a chalkboard with a force of 1.5 newtons. So we've got a magnet here. All right, that's my magnet, and I'm sticking with it. Now, we'll just put a circle around the magnet so it's easier to kind of think of it as a kind of a unit. Now, this is with the chalkboard, if you will, on its side. All right, now what are the forces that are happening with this bad boy? Let's think about this. First of all, let's make a note here. The acceleration is 0 meters per second because it's not moving, all right? And so since it's on the chalkboard on its side, all right, then the magnet, if you will, is hanging right here, right? This is the ground right here. And so what you've got is you've got the force this way, and we've got a force this way, right? And it's with 1.5 newtons, so the force that is being held to the chalkboard is a force of 1.5 newtons. The force of the magnet, if you will, is this way, and that's 1.5 newtons. And then what's holding it opposite is the normal force, and that also is, that's a point right there, 1.5 newtons. Okay, so that's side by side. The first one is up and down. This last one's an interesting one. So you're helping install an 11 kilogram decorative beam to a ceiling. You apply a force of 170 newtons upward. So you've got a beam right here, right? And you are pushing up on the beam. We don't draw up. Technically, you're pushing right here, right? But you're applying a 170 Newton force, and this is, if you will, the force of your hand or your body or whatever. We'll call it the force applied. All right? But what do we also know is going on? Is we also know that there's always the force of gravity. And the force of gravity would be equal to m times g, so which would be equal to, the mass is 11 kilograms times 9.8. And that comes out to, when you do all the mathy stuff, that's 100 and, we'll just say 108. I'll round, 108 newtons. But we have to have balanced forces, right? So how do I do that? So we have to have balanced forces. So this is 170 because it's a static beam, right? And this is 108. So I need another force. And where's the force going to be? That force is going to be in the downward direction, right? So this upward force must equal the downward force. So I could say 170 newtons is equal to this number here. What? 108 newtons plus, if you will, the other force, the perpendicular force to the board, which is the normal force. So I simply solve for the normal force by subtracting 108 from both sides, and I get the normal force to be equal to 62 newtons. Now, it's important. We could say it's actually negative 62 because the force is downward, or you could say 62 newton down. It's important, right? Because the forces have to balance if the object is not accelerating. Probably the most classic type of problem that we see is bathroom scale problems. And this is an interesting one, is that we are now at an elevator, right? So you're on an elevator on a bathroom scale, all right? So you're in the elevator and there's a scale right here, right? And you're standing on the elevator, all right? And the person weighs 75 kilograms. So the force of gravity, okay, that's going to be equal to mg. Now let's figure that out. 75 kilograms, right? So F of g is 75 kilograms times 9.8 meter per second squared. And that comes out to be 735 newtons. So the downward force is 735 newtons. Now, the first example right here, the elevator is stationary. Then if the elevator is stationary, then the net force, of course, has the normal force, which will be opposite. So in this case, the net force, or the normal force, pardon me, is going to have to be equal to 735. All right, so that's an easy one, but it gets more complex. All right, so when I go to, it's going to accelerate. The elevator is accelerating upwards at 0.25. So now I'm going to simplify my diagram here. So we are accelerating upward, okay, so the force of gravity, okay, F of g doesn't change because the cat still has a 735 newtons. So what have we got going on with this one? Since the acceleration, the net acceleration is 0.25, what we can say is the force net, if you will, right, is equal to ma, right, which is equal to the normal force plus the F of the gravity, making sure that they're opposite and equal, right? One will be positive, the normal force, if you will, is going to be upwards. But we've got this acceleration thing going on. So we want to do this ball game right here. So what I'm going to say is I'm going to say 75 kilograms times 0.25 meters per second squared, right? That's ma in this case, right, would be equal to the normal force plus the force of gravity. And we're solving for the normal force. Now what we know is force of gravity is 735. Get our calculator out. 75 times 0.25 is, we're going to kind of round this, that's 19 is equal to F of N plus 735. So what we're going to do is we're going to subtract 735 from both sides, right? And 19 minus 735 equals, so the normal force here would be equal to negative 754. And I realize I've just got my signs wrong. The force of gravity is actually negative, so if this is actually negative. Anyways, then you'll end up with positive 754. I messed up. So the normal force is actually bigger because of the acceleration. The normal force is 754 newtons. The gravity force is negative 735 because, of course, it's down. Notice that it's bigger, right? Let's do the reverse. That's when it's going upwards at 0.25 meters per second. What if it is going downwards? So here's my elevator system, if you will. And now the acceleration is going downward at 0.6 meters per second squared. So that means it's going to be a negative force. I'm going to use the same equation, folks. F net is equal to Fn plus F, the normal force, plus the force of gravity, right? Now, so note, these have to add up to 0, right? Positive and negative. Well, actually, that's not completely true. The net force has to add up to 0. So the net force we know is mg, or ma, and so that's going to be equal to 75 times 0.6, but it's actually not 0.6, it's negative 0.6, right? Is equal to the normal force, which you don't know, right? Normal force, we're trying to solve for that. The normal force, which is upward, and this is the force of gravity, plus negative 735. And then we're going to say 75 times 0.6 is negative 45, negative I should say, is equal to normal force plus negative 735. All right, so in this case I would add 735 to both sides, right? And I get the force normal to be 690 newtons. Here's sort of the big sort of takeaway. If you were to summarize all this, right? If F of N is equal to F of G, that's true. This is true. F of N equals F of G if A is 0. But if the normal force, think about this, if the normal force is greater than the gravitational force, then A is up, right? Goes up. And the force normal, if it's less than the force of gravity, if, these are if, by the way, if A is downward. What if the elevator is moving upward at a constant velocity? This is a super easy question because we think it's moving upwards at a constant velocity. It's not accelerating. If it's not accelerating, then the F net equals Fg plus F normal, and they are going to be equal to opposite because there is, since it's not accelerating, then the F net, if you will, is 0. Next up, what you're going to do is do some problems that kind of work you through this, and I think it'll come more clear in class as you're working through this. It's really about drawing forces. I didn't give you one where you've got angles and junk. That's going to come particularly later, and you'll see that, but it's all about the equal and opposite. We're just applying Newton's third law, and second law for that matter, together to solve for this force. The table is pushing back on the book, or on your hand, right? And then we want to talk about how much that actually is. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.